Thank you, viewers. This is Mr. Dingo, and today I want us to learn about Calculus 1, that is differentiation. We know calculus is a very wide chapter that carries both differentiation and integration. But today we want to start looking at differentiation. And before we go further into this concept of differentiation, you want to understand what differentiation is all about. Now, in your earlier studies, you learned about equations of straight lines, equations and gradients of straight lines, where we know that for straight lines, the gradient m is always constant. I'm also aware that you have also learned about graphs, especially graphs of quadratic graphs or cubic graphs, and you know that for quadratic graphs and cubic graphs, the gradients are not constant. The gradient must be calculated when we look at an instantaneously. Instantaneously, meaning that we can only get the gradient of a curve at a point. If this is a curve, we know the gradient here cannot be the same as the gradient here, and that way. So we can get the values of the gradients at each value of x, meaning that at a point it is something that is keeping on changing, and that is where differentiation comes in. So differentiation is basically the study of rate of change. The study of rate of change, that is differentiation. Study of rate of change. Study of rate of change, especially for cases where gradient is not constant. Cases where gradient m is not constant. Where the gradient rate of change is constant, then we don't need differentiation as such, but we can still use it to particularly get the answer. But here in this case, it's very, very important for cases where the rate of change is not constant. And when the rate of change is not constant, then it means we are dealing with curves. And I want us to know that rate of change is a term that is used in very many subjects, probably in chemistry, biology, in physics, in mathematics. But here we know that rate of change here in math may also mean gradient or the slope of a curve at a particular point. So we are going to talk about the rate of change or the slope of a line at a particular point, and that slope we are going to call it m. The value will be m. So we want to derive how do we really calculate the gradients or the rate of change of curves. We know that of straight lines, that is very simple, especially if you write equation in form of y equals to mx plus c, then you know the gradient is directly m. And sometimes we know that if you have 2 points, then you can say change in y over change in x will give you the value of m, which is our gradient. That is very easy and quite direct. But today we want to look at how do we calculate the rate of change, or gradients of curves. So in front of you here I've drawn a sketch of a curve y equals to x squared, and this curve we want to be able to get the expression of its gradient. We know we cannot get the gradient because we want to get expression which is going to be used for the whole gradient at any particular point. But if we know the value of x, then you can get the gradient at a point, at a particular point. Now, I want us to know that I've put here point A and the coordinates of point A with me here. Now that we know that this one is x and y, the value of A here, or the coordinate of A, will be x, y. That is the coordinate of my point A. So now that we know the coordinate of point A, let us get the coordinate of point B1, which is, we know that the x-coordinate of B1 is x, plus change in x, comma, the coordinate of y here will be y plus change in y. Now you realize that the line I've drawn here, line AB1, is not a tangent. It's not a tangent, and therefore the gradient between A and B is simply average rate of change. But we want to get instantaneous, meaning the rate of change or the gradient at exactly point A. Now I want you to know that as you move from B1 along the curve to B2, the value of the gradient here, the value of change in y, let me say change in y1, and the value of change in x will also be change in x1. You realize that the new change in y, once we come from A, B1 to B2, which is much more closer to A, the value of these changes in y and change in x reduces. If I come to B3, probably here, B3 here, and I draw this line, you realize that again, let me say change in x2, change in y2, and change in x2, these values keep on dropping. If I move here, it will be much more smaller. If I come and reach here, these changes, change in s and change in y, will change to 0. And therefore, that is what we want to derive here and see how do we then calculate the derivative or the expression for the gradient. Assuming at A, at coordinate A, the equation is very clear. Y equals to x squared. That is the equation at coordinate A. What about if I were to get the coordinate at B1? At B1, the coordinate therefore will be, knowing that I have x equals to y equals to x squared, but we now know that the value of x at that particular point, the new x is x plus change in x, and the new y is y plus change in x here, sorry, this is change in y. So we can simply come here and substitute where x is, we put that, and where y is here, we fix that one there. So if I do that, we'll find that y square y, which is y plus change in y, equals to x squared, and our x squared is x plus change in x squared. That is what we have. From here, after substituting, we come down there. So if I move downwards to be able to open this, we know we can open this bracket, y plus change in y equals to x squared plus 2 times x times this, that is plus 2x, 2x change in x plus change in x squared. That's what we have if we open that particular bracket. Now that we have this one here, I want to have change in y, because we know in our previous lessons we have learned that gradient m is given by change in y over change in x, and that is what I want to go to. So in this case I want to take y the other side, so I'll get change in y equals to x squared plus 2x times change in x plus change in x squared minus y. But we know that y equals to x squared. So where y is, I'll quickly substitute with x squared. So I'll get change in y equals to x squared plus 2x times change in x plus change in x squared minus x squared. But you know that x squared minus x squared will be 0. So finally, change in y equals to, we know that this one has gone and that one has gone. So we'll have 2x times change in x plus change in x squared. But we know that now that we have this kind of expression, I want us to get this kind of expression because we are looking for gradient of a curve. So for me to I have change in y here. For me to have change in y over change in x, I have to divide everything because there's change in x on the other side. So I have to divide everything by change in x for me to get gradient. So I'll say here gradient is now change in y over change in x equals to, if I divide everything by change in x, change in x, I expect that this change in x will go. So what will I have? I'll have 2x here plus change in x squared divided by change in x, we'll get change in x only. That's where we have. Now let me see. I will say that as b1 tends to a, meaning that as b1 tends to a, what is happening? Tending to a meaning what I've explained here. We come from b1 to b2. What we see is that the change in x and change in y are dropping. But in this case, we have only this change in x here. What is happening to it? It is moving closer. As the b2 is moving to b3, we have the change in x becoming very small. If you come to this, maybe let's say this is b4 here, this is b small. When it comes, let's say b5 here, where now the change in x has become 0. So we say that as b tends to a, or as it approaches a, the value of this one tends to 0. So we can therefore say once it tends to 0, then this change in y over change in x changes from just being change to d. That now we can say that the gradient now will going to be dy dx equals to 2x plus 0, because we now know that now b1 has approached a, and therefore the value of change in x here has now disappeared. So we can therefore say that if y equals to x squared, then dy dx equals to 2x. Let us pause a little and see what we have done. The expression for this curve is, the equation for the curve was y equals to x squared, but the gradient now, the gradient function is 2x. How did we reach there? So let's try to see this thing. Y equals to x squared, but dy dx equals to 2x. What happened here? What happened here is that we don't have to do this every time we want to differentiate. We can simply now say that, okay, the power of the x here has been moved here, and that's why we can see it here. And then the 2 that remained here, we subtract 1. So that when you subtract 1, you remain with 1. So we should actually have dy dx is 2x power 1. So we can say, in conclusion, we can therefore say that if you have x, if you have an expression going this way, y equals to x power n, where n is the power, in this case our n was 2, then dy dx equals x n x power n minus 1. This will give you the rule for the expression for the gradient function after you differentiate. So let us see. If I have y equals to x power 3, if I have y equals to x plus 3 as an example, what do we have here? If you have to get dy dx will be 3 is our n. It comes here, so it will be 3x power 3 minus 1. That will be 3x power 2. That will be the gradient function. Now, this is a much more simpler case. What about if the x here as a coefficient? If it has a coefficient, we are going to be talking about a totally different case. If it has a coefficient, let's say coefficient a, this is example 1. What about if we have example 2 where we have y equals to ax power n? You realize that in this particular case here, the coefficient was 1. But in this case here, the coefficient is a, meaning it's a number. Could be a positive number, negative number, any number could be there other than a number positive 1. So if you have this particular case, the same thing applies. We take the n here, we multiply by a, then the n there we subtract 1. So if y equals to a x power n, then dy dx will be a, let me say n a x power n minus 1. It doesn't matter which one comes first. The product is what we are caring about. It must be n times a. So that if I give you an example like y equals to 2x power 5, how do you get dy dx of this expression? So it will be dy dx equals 2 times 5 x power 5 minus 1. That will be 10 x power 4. That will be the expression for the gradient function. Viewers, that is how you get the gradient function of different expressions or different equations. Once more, I want us to move to differentiation, which we started in our last lesson, to be able to dig deeper to see different types of equations. We know that we were able to differentiate a single term equation, which is not really the practical things you are meeting in exams. Today I want us to move to differentiating what we call a polynomial. If you have a polynomial simply means an equation or an expression of an equation that with different terms. For example, I can say y equals to x squared plus 3x plus 2. So if I have this particular expression and I want to be able to differentiate it, we are just going to do the same thing we have done, meaning we are going to differentiate each term independently. And in this particular case, if I say now let's get dy dx, let's see. This one we have seen how to differentiate it. It means we are going to take these two here. So we are going to get 2x power 2 minus 1 plus, we go to the next. We are done with this one. That is the differential or the derivative of 2a or x squared is 2x raised to power 2 minus 1. What about 3x? 3x, I normally say this is a derivative of a straight line or a linear equation where we can say let's have y equals to 3x. If you have y equals to 3x and you have to differentiate that one, what happens? We know that the value of x here is 1. If it is x, then it is x power 1. So we can therefore say, if I have this one, I have to differentiate dy dx. Then if I bring this, it will be 1 times 3x power 1 minus 1. So this will be 1, or 1 times 3 is 3x power 0. So realize that x power 0 is 1. So if x power 0 is 1, so meaning that we will have 3 times 1 here. So we can say that in this particular case here, we'll have 3 times 1 into x power 1 minus 1. What about the derivative of a constant? I say this is a constant because there is no variable x there. So it's a constant. Derivative of a constant, let's see. If we have y equals to 2, and we have to get dy dx. If you have 2, y equals to 2 is the same as 2 times 1 because 2 is the same as 2 times 1. I say 2 times 1 is just 2. So if I have that, then I can say, in this case, for me to have 2 multiplying 1, then this could have been x power 0. It could have been x power 0 because 1 is the same as x power 0. X power 0 is 1. So let's develop it as we go down. If you have now to differentiate this one here, what do we get? Dy dx will get 0 times 2 x power 0 minus 1. So we'll be able to get, but we know that anything multiplied by 0, because 0 multiply 2 will multiply x power negative 1. Anything multiplied by 0 is 0. So we can get many things from here. We have seen the derivative of a linear equation, which we have said will be the same as the coefficient of x. When I come to the derivative of a constant, it is 0. A constant is a constant, whether it's a million, whether it's 10,000, whether it's -2, whether it's whatever number, the derivative or the gradient function of a constant is 0. We will help you note those particular ideas The derivative of a linear function is the coefficient of x. The derivative of a constant, in this case, the value of the number in the equation without x or without a variable, is what we call a constant. And I said that will be 0. So let's see. This will be 2x, because x power 1 is x. Then plus, this will be 0. And x power 0 is 1. So we'll have 3 times 1 is 3. We can't add 0. So this will be our gradient function of this particular polynomial. That is our example A. What about if you have example B? Y equals to 3x power 3 minus 2x power 2 plus 4x minus 10. That is a polynomial. Let's try to differentiate it. And I've said before, this one, dy dx of this expression or this equation will be 3 multiplied 3 is 9. Let's go very fast now. X, 3 minus 1 is 2, minus 2 times 2 is 4. X, 2 minus 1 is 1. I don't have to write that one. Plus, this is a linear equation. I said the gradient or the derivative function of a linear equation will be the coefficient of x, which is 4. Then minus 10. 10 here is a constant, and I said the derivative of a constant is 0. I don't have to write that 0, so I'll just say the derivative of this polynomial is 9x squared minus 4x plus 4. Viewers, that is very okay. I want to move to differentiating fractional expressions. Differentiating fractional expressions. Fractional expressions. Differentiating fractional expressions. Sometimes we have an expression which is a fraction in nature, and we have to deal with it. So let me say example A. If you have y equals to 1 over x squared. If you have y equals to 1 over x squared, this is a fractional equation. The first thing we have to do is to ensure that we get the reciprocal of this expression. We get the reciprocal of this expression, we will still get the equivalent, because we know the reciprocal of this is x power 1. So reciprocal of this will be x power negative 2. In indices, you learned that 1 over x power n is the same as x power negative n. So that's what the concept we are applying here. It means that if you don't know indices very well, this will be a challenge. So after we remove the fraction, or we get the reciprocal to do away with the fraction, then we can get dy dx. Viewers, don't make a mistake of saying dy over dx. That is not how it should be. It should be dy dx. dy dx. If you say dy over dx, someone will know that you actually are trying to see math the way it appears on the board or the book. That's how you want to read it. So when we are having this particular expression now, we follow the same rule. Negative 2 comes here, so we'll get negative 2x, negative 2 minus 1. So that will be negative 2x power negative 3. That is what we have as the derivative of that function. What about if I say b y is equals to 1 over 8x power 3? This is very funny. I would be very afraid to carry 8. But what I can do in this particular case is to separate. I know this will be the same as 1 over 8 times x cubed. If I have that, then I can say y equals to 1 over 8 times 1 over x cubed. So 1 over 8 here, I will not interfere with it, to remain there. But I will just have to do something about 1 over x cubed, where I will just again do the reciprocal. So I'll get y equals 1 over 8 x power negative 3, if I do the reciprocal, and then we move further to be able to differentiate. I say dy dx will be negative 3 coming here will be negative 3 over 8 x 3 minus 1, negative 3, sorry. So this will be negative 3 over 8 x power negative 4. That is the derivative of that particular function. So viewers, we have seen how we can deal with fractional expressions. What about if you have to deal with the derivative or differentiating SADs? Differentiating SADs. Now we know what SADs are. SADs are actually the roots, the cube roots, or the square roots, the fourth roots of non-perfect squares or cube roots or whatever. For example, if you have an example here, we can say we have y is equals to SAD x. That is an expression as well. So y is equals to SAD x. First, we have to use the concept of the knowledge of indices to change it from SAD into an index form, which is going to be y equals to the square root of x is x power a half. We know that the square root of x is x power half. The cube root of x is actually x power a third. The fourth root of x is actually x power a quarter, and so on and so forth. So if we have y equals to the SAD x, then we can be able to differentiate now by saying dy dx will be, we bring a half, we multiply here, so it will be a half x power half minus 1, and that will be a half x power minus or negative half. This will be the derivative of this particular function. What about if I have y equals to 3 SAD x? 3 SAD x in this particular case means that first we convert this SAD x into an index form, so it will be y equals to 3x power a half. Then when you differentiate dy dx, you get a half times 3, a half times 3 x power a half minus 1. That will be 3 over 2 or 1.5 x power minus or negative a half. That is the derivative of that particular SAD. So viewers, if you are dealing with, we have talked about polynomials, we have talked about fractional expressions, we have talked about SADs. Now we can also be told to differentiate functions. Let me call them other functions, because I don't have a specific name for them. Let me say other functions. So under other functions, I want to give an example of if you are asked to differentiate a x plus 2 into x plus 3. Now viewers, at this level, I'm not going to tell you the direct method of dealing with this particular case. There are ways of doing it directly, but I want us to go to the very simplest method, meaning we have to first of all expand the expression. We expand the expression first, that is x into x plus 3 plus 2 into x plus 3. That will be x squared plus 3x. 2 times x is 2x plus 6. Then we have a like term here, 3x plus 2x, so we'll get to sum that, that is x plus 5x, x squared plus 5x plus 6. So we have, sorry, I left y here. So this is y equals to y equals all this thing equals to y. So let's differentiate dy dx for this. Again, this is a polynomial function, so we are just going to do the same thing. We bring 2 here, that is 2x power 1, and if it is 2x power 1, I don't have to write that 1, plus the derivative of a linear equation will be the coefficient of x, which is 5, plus the derivative of a constant, which is 6, should be 0, which we don't have to write. So this is going to be the derivative of that particular function. What about if we say b, the derivative of y equals x squared plus 5x minus 5x plus 6 divided by x plus 2. If you have this kind of thing to solve, first we have to remember quadratic equations and also simple expression for us to go forward. So the first thing, we are going to factorize the numerator before we are able to get the derivative. So factorizing the numerator here, I'm going to open 2 brackets, and these 2 brackets I'm going to say the square root of x is x. So in this bracket I'm going to put x. But I know that there are 2 numbers that if I multiply I must get a positive. It means these numbers must be negative. So those 2 numbers must be negative. If those 2 numbers are negative, the next thing I will look at those 2 numbers that are negative. When I add them, I should be able to get negative 5. So 2 negative numbers added to give negative 5 probably should be negative 2, negative 3. So I'll say when I can put 2, when I put 3, I can put the other side the other way. And then the denominator to be said, it is x plus 2. I think this is going to present a difficult situation for us. But assuming we had this one as negative 2, this could be what I was intending to do. If you have that is equal to negative 2, then what could happen here is that we would simply simplify this. So then y will be x minus 3. When y is x minus 3, and then you are told to get dy dx, this is a constant. It's a constant, or not a constant really, but an expression or a linear equation where the coefficient is 1. And we say that if you have that particular case here, you take the coefficient as the derivative, but this is a constant with a derivative of 0, and therefore dy dx in this case, particular case, which is the gradient, is 1. It means that if the gradient dy dx is a constant, then that is very key to us. It tells us that the equation we are dealing with is a linear equation, and you can see that y equals to x minus 3, which could also translate to y equals to mx plus c. And if mx plus c, then m is the coefficient of x here, which actually is 1. And we have actually used differentiation to establish that kind of relationship. I want us to go to how to calculate the gradient of different curves at given points. Sometimes, and this is the most common thing you are going to meet in examination, if you have a curve or an expression of a curve and you are told to calculate the gradient of that particular curve at given points of x or at a given coordinate. And let me give you an example here. If I have an example of this particular case, examples 1, find at given coordinates. Given coordinates. What about if I have example 1, y equals to 2x squared plus 4, and the coordinate is 1, 5. So we want to get the gradient of this curve at the coordinate 1, 5, meaning that we have actually the value of x at which we need to be able to calculate this gradient. So the first thing, if I need gradient, I need to calculate gradient function, and the gradient function is dy dx. This is the function for the gradient for the whole expressions, and the gradient function here will be, I bring this will be 2 times 2 times 2x or 2 minus 1, which is going to be 4x. We know the derivative of 4, which is a constant, is 0, so we don't actually need to include the 0 in the gradient function. Now if I have the gradient function as 4x, then I need to get the actual gradient, which is m. Gradient m, now that I know the value of x is 1 and I know the gradient function is 4x, then I simply substitute 1 where x is. So I'll say that the gradient now is 4 times 1, which is 4. So the gradient of this line 2x squared plus 4 at x equals to 1 will be 4. You see how easy it is? B, if I have y equals to 3x squared plus 2x minus 5. If I have that and I need to get the gradient of this curve at, let me say, at 2, -1. That is the coordinate at which I need to get this gradient. So what I'm going to do first is to get the gradient function, which is dy dx. That is dy dx. And now I want to go very fast. 2 times 3 is 6. 2 minus 1 is 1. So it is 6x plus the gradient of a linear equation is the coefficient of x, which is 2. And the gradient of a constant is 0. So we don't have to include that. If I move forward to get m, m is now going to be when I substitute the value of x here to get the actual. So this is x 6 into x is 2 in this equation, and then plus 2. So this will be 12 plus 2, which is 14. So the gradient of this curve at x equals to 2 is 14. That is fairly easy. What about if we go forward to say get the value of the gradient, that is b. Let's go to c. C is y equals to 5 sad x, and x, let me say the coordinate is 2, let me say 4, 0. If you have y equals to 5 sad x at the coordinate 4, 0, then the first thing I said for sads, we said dy dx here. No, let me first of all change this one into a index form. That will be 5 equals y equals to 5 x power a half. So y will be this will be 5. Let me say dy dx now. Dy dx will be half times 5. Half times 5 x power negative a half. Negative a half. So we'll get that one. We'll do 5 over 2 x power negative a half. So what we need to do here is let us substitute 4. This 4 is the value of x, where in this equation that is 5 over 2 in bracket 4 power negative a half. Now viewers, we know in indices that if you get the reciprocal of this number, this power will change to positive. So we can actually say 5 over 2 in bracket 1 over 4 power half. So that is now fairly easy. Now we know that 1 half is the same as sad or square root. So I can say this is 5 over 2 sad a quarter, which is going to be 5 over 2 times 1 over 2, and that particular thing will be 5 over 4 as the gradient of this curve at the value 4, 0. Now we have seen how to substitute the value of x into the equation. Sometimes they will not give you the coordinate, they'll just give you at x equals to something. Let me give you that question example. For example, if you have dy equals to 5x power 3 minus 2x power 2 plus x at x equals 3. That's what we have at x equals to 3. That's very direct. It's the same thing as if you have the coordinate. At the coordinate, we are only selecting the value of x. But in this case now, we have the value of x given to us very directly. So we just again get dy dx, and that will be 15x power 2 minus 4x plus 1. But we know that m, we have to substitute 3 where there is x, so that is 15 into 3 squared minus 4 into 3 plus 1. This will be 3 squared is 9, so 15 times 9 minus 12 plus 1. So this will be times 9 minus 11. You can solve that and get what the gradient will actually be. So viewers, we have looked at a case where we have the coordinate. We are asked to get the gradient. We want to move forward to look at the second part of the lesson of today, that is finding coordinates of a curve given the gradient. Now, as you can see here, in this case, the previous cases we have looked at a case where you are given the curve and a coordinate and they want you to find the gradient. But in this case, you are given the gradient and the equation of the curve, then they want you to be able to find the coordinates. So very first what we do in this case is to find the gradient function. Gradient function is dy dx. So dy dx of this equation will be 2x plus 3. So if the gradient function is 2x plus 3, but we know the gradient is m, and m in this case is 9, so we can say that the gradient function here will be equivalent to the gradient which is 9, that is 2x plus 3 equals 9. So we solve this equation, we will get 9 minus 3, and 2x here equals 6. We divide by 2 both sides, x equals 3. So the value of x for this equation is 3. We need therefore to get the other value of y, which is y. The value y is x squared plus 3x plus 2. But we know x is 3. So y in this case will be 3 squared plus 3 into 3 plus 2. We know 3 squared is 9. 3 times 3 is the same as 3 squared, which is 9 plus 2. So 9 plus 9 is 18 plus 2 is 20. So finally, the value, the coordinate, the value of y coordinate is 20, the value of x coordinate is 3. So the coordinate is written this way, 3, 20. That's the coordinate on this curve where the gradient is 9. Then the first part of this curve is find dy dx. So for us to find the dy dx of this equation, we know the first thing we have to do with this equation is to be able to expand it, open the bracket, because the equation is y equals 2x minus 3 squared. So if that's the equation, what we do here is we open the bracket. I want to go very quickly to open this bracket. That is 2x minus 3 into 2x minus 3. This will be 2x into 2x minus 3 into 2x minus 3. So we open the bracket. It will be 4x squared minus 6x plus 9. So y here equals to 4x squared minus 12x plus 9. That is the value of y. We know that if you are good at math, you'll be able to know how to open this one very directly without following the long method. That will be, we take 2x squared, will be 4x squared. That's the first term. The second term will be, we take this power as 2, so it will be 2 times 2x, which is 4x, times negative 3. So 2 times 2x is 4x, times negative 3 will be negative 12x. 12x. Then finally the third term you square, like you square the first term, so negative 3 squared will be plus 9. Plus 9. That is exactly what we have there. So if you know how to open directly using that method, that is exactly what you will do. But if you don't know, please follow the long method so that you are sure to be correct. Now we have not answered the question yet. We have just expanded the question so that we can factorize to be able to get dy dx. Dy dx in this case will be that will be 8x minus 12. We know that we bring 2 here, we multiply, then we subtract 1. Then here it is 12x. This is the derivative of a constant. Linear equation will be the coefficient of x. For this one, the derivative is 0, so we leave it there. The second part of this question be find the coordinate is 4, for which the gradient is 4. Now we have done good here to get the value of the gradient function, which is 8x minus 12. If you remember what we did in example 1, once you have the gradient function here, you equate it to the gradient that is provided for you here so that you find the value of x. That will be 8x minus 12 equals 4. So that will be 8x equals 4 plus 12. And that is 8x equals 16. So if 8x equals 16, then divided by 8 x is 2. Still, we have got the x coordinate. We are supposed to now go further to get the y coordinate. And for us to get the y coordinate, you know that the value of y, the curve A is 2x 2x minus 3 squared. That is the value of y. So I'll substitute where x is, I'll substitute the value of 2, which is 2 into 2 minus 3. Everything in this bracket squared. That will be 4 minus 3. 4 minus 3 squared. So 4 minus 3 is 1. 1 squared is 1. Now remember that you can still substitute the value of x here. This is still the value of expanded form of y. So if you are substituting the value of x here, we know the value of x is 2. So this will be 2 squared is 4. So it means 4 times 4 is 16. Minus, if you substitute the value of x here to be 2, then 2 times 12 is 24. Then plus 9. So we'll be able to have 16 plus 9 is 25 minus 24 is 1. Exactly what we have got here. So once we got the value of x and y, then we write the coordinate, which is x2, y1. This is the answer for the part of the question that is part B. Now I want to move to the next question, example 3. I want to go to example 3, and the example 3 is here. Example 3 is here. 3, find for which the gradient is 4. So again, this equation is very important. We need to first of all get dy dx for the curve. Dy dx in this case is, if I get dy dx of this case, will be 2x squared plus 2x. But I know that this one is 4 because this is gradient, but this is the gradient function. So 2x squared plus 2x equals 4. I see we end up with a quadratic equation. If I bring this one here, it will be 2x squared plus 2x minus 4 equals 0. So we have a quadratic equation. this quadratic equation, you can simplify further by dividing by 2. Dividing by 2. If I divide by 2, I'll get x squared plus x minus 2 equals 0. Let me factorize the product of numbers that if I multiply, I get 2, and when I add, I get 1. So these numbers, probably the bigger number must be positive, and I'll say, let me take 2 and negative 1. If I multiply 2 by negative 1, I get negative 2. If I add 2 minus 1, I get 1. So x squared is x, and I know that the bigger number is the positive, so I'll say plus 2 here, and I say minus 1 there, equals 0. So in this case, I have two values of x. X is negative 2, and x can also be 1. It means that the gradient of this function is 4 at actually 2 different points. So if we have these 2 different points, the first thing we need to do is to get the value of y when x is negative 2, and then get the value of y when x is 1. So I'll come back to our equation here, which will be able to help me get the value of y, and then I say y. Let me say when x is 2, then y will be 2 over 3 into x, which is negative 2 here. X is negative, sorry. Negative 2 cubed plus negative 2 squared. So this one, let's do it very quickly. This is 2 divided by 3 times negative 2 cubed. That is negative 16 out of 3 plus 2 squared obviously is 4. So if we add 4 there, we get negative 1 and a third. Negative 1 and a third is the value of y. So the first coordinate is x is negative 2 and y is negative 1 and a third. That's the first value of y. Let's go for the second value of y, and we say when x is 1. I think that's what we got. Y will be 2 out of 3 of 1 cubed plus 1 squared. Y in this case will be 2/3 plus 1, which is the same as 1 and 2/3. That's the value of y. So the new coordinate, the next coordinate of this in this point will be 1, 1, 2 over 3. Those are the two coordinates of the curve. On the curve, y equals to 2 over 3x cubed plus x squared, where the gradient is 4. So it means that if we were to sketch this curve, we draw this curve on our graph, and then we determine where the points on the curve where the gradient is 4. Those coordinates on the curve where the gradient is 4 must be either when x is negative 2 or when x is 1. Viewers, thank you very much. That is the end of the lesson of today. We'll move forward next time to look at equations of tangents or equations of normals. Thank you.